Hi, it's Moser with a quick tutorial on where the electrons are. Part 1, Orbital Notation. So by the end of this video, you should be able to write the electron configuration for any orbital in a form that we call orbital notation. You'll end up learning 3 forms. This is the first. What you already need to know, well, you need to know what shells, subshells, and orbitals are, as well as how to find the number of electrons in an atom of any element by using the periodic table. Okay, let's just do a quick review. You remember that we've held over from the old Bohr model of the atom the idea of main energy levels, though in the quantum model things go considerably deeper and get considerably more complicated. But we remember that n equals 1 is our main energy level 1, n equals 2, main energy level 2, n equals 3, blah, blah, blah. It just goes on and on and on. What we've added in the quantum model is that at n equals 1, main energy level 1, we have the 1s subshell, which is made up of the 1s orbital. And that at n equals 2, main energy level 2, we have the 2s subshell, made up of a 2s orbital, and the 2p subshell, made up of the 2px, 2py, and 2pz orbitals. On the third main energy level, n equals 3, we get a 3s subshell, a 3p subshell, and a 3d subshell, made up of 1 orbital, 3 orbitals, and 5 orbitals respectively. So, what we want to be able to do is figure out where in the electron, in the atom, these electrons live. So we want to look at this structure and basically write an address for the electrons in the atom. We call this the atom's electron configuration. Now, there are different ways to write electron configurations, and you're going to learn 3 methods before this chapter is over. There also happen to be 3 rules that allow us to figure out the electron arrangement for any element. The first rule is what I like to call lazy electrons. In other words, they're not going to do any more work than they have to. This is actually formally known as the Aufbau Principle, and it just says that an electron will occupy the very lowest energy orbital that is able to take it. So 1s is the lowest energy orbital. 2s comes next, and then 2p, obviously 3s, and then 3p, and then things get a little bit weird. We'll get to that. Did I mention that things got a little bit weird? This is called the orbital filling diagram, and you're going to actually need to commit it to memory. Well, you'll just need to know how to write it. Actually, the subshell filling diagram. It shows the order in which the subshells fill. Perhaps easier if we write it out together ourselves. So we start by just writing our s's. 1s, 2s, 3s, 4s, 5s, 6s, 7s. That's all the further we need to go with that. And that's easy. Every single main energy level has an s subshell. Well, then we start with our p's. They start at 2, so 2p, 3p, 4p, 5p, 6p, 7p. Excellent. Then we start our D's. These, of course, start on the third main energy level, so we go 3D, 4D, 5D, 6D. Now, we could write the 7D subshell, but here's the thing. We aren't actually aware of a single element that exists, that we know of, that has any electrons on the 7D subshell. So while we can write it, we really don't need to. We do have to do our F's, however. So these start with 4F and 5F. We could write 6X, but again, we don't know of anything that exists on the 6X subshell. So we very often stop the diagram like this. You are welcome to continue it if you would like. There. Does that make you feel better? You'll see in a moment why it really doesn't matter that we wrote those. I'm going to take a nice, bright, contrasting color, and we're going to draw a line right through these. And what you're going to see, and sometimes we put a little arrow on the end, to remind us which way we're going. That's always helpful. What you're going to start to see is that this arrow cuts very neatly. See, this is why we didn't need those guys. We'll just scribble them out. The arrow cuts very neatly through the subshells in the order of increasing energy. So 1s is the lowest energy subshell, followed by 2s, followed by 2p, followed by 3s, followed by 3p, but then something strange happens. The 4s subshell is actually lower energy than 3d, and because of that, it fills before 3d. You would never get that without knowing to draw the subshell filling diagram. After 4s, we fill 3d, then 4p. Oh, it just gets weirder, doesn't it? Then 5s, 4d, 5p, 6s, 4f. Holy cow! Yeah, it's pretty strange out here in the deep end. That's why you need to learn how to draw the subshell filling diagram. So let's see what that looks like in practical real life. Oh wait, we can't, you say? Because we aren't quite sure what the other rules are, you say? Yeah, you're right. Okay, so let's just keep this in mind as we go on to Rule 2, which I like to call, you stay on your side and I'll stay on my side. This is the Pauli Exclusion Principle, named after Wolfgang Pauli, yet another German particle physicist. What this says is that no two electrons in the same atom can have the same set of 4 quantum numbers. Now, we don't talk much about quantum numbers at this level, but what it really means is that each electron in an orbital has to have a different designation somehow. So if you have a 1s orbital, and of course an orbital can hold 2 electrons, we designate one as having spin up and one as having magnetic spin down. And we represent them with these little sort of half-headed arrows. Well, that's easy enough. On to Rule 3, which I call, I don't want a roommate. Rule 3 just states that orbitals of equal energy are occupied by 1 electron apiece before any orbital gets a second electron. If you can imagine an apartment building or a dorm, a situation that some of you may become familiar with in a few years. As you're moving in and you get to pick any room you want, the first principle is when you're carrying all your stuff and there's no elevator, you take a room on the bottom floor if one is available. So, when you get there with all your stuff and you're the first one there, and there's space on the lowest energy level, in other words, the floor that requires you to climb the least, you're going to take it. Now, if you get there and there's already one person in that room, you might weigh your options. Well, let's see. I could climb stairs, or I could just have a roommate. Okay, fine, I'll take a roommate. I'm not climbing any more stairs than I have to. Well, if you get there and the first floor is full, you're going to go to the next lowest level. If we extend our metaphor, this would be the 2s orbital. And again, when you arrive there and find one person in the 2s apartment or the 2s dorm room, rather than climb the stairs to 2p, you're just going to go ahead and suck it up and take a roommate. But when we get to 2p, when you find all 3 of these rooms of equal energy, equal height, equal number of stairs required to get there, open, you're going to take the first one you see. Well, it may well be that the next person to show up, well, they're not going to want a roommate if they don't have to have one. So, each one of these rooms will get one occupant before any of them take a roommate. But once there's one occupant in each room, the choice of taking a roommate, overcoming the repulsion of having a roommate, and that's really what it is, or climbing stairs to the next energy level, you can overcome your repulsion. You can live with a roommate. It's not until every single available space on that 2p subshell is full, I mean floor 2p, that any college student, or electron is willing to take the extra effort required to climb to the next level. In this case, the 3s subshell, or the third floor. Okay, now let's do this with an actual atom using the 3 rules to write the electron configuration in orbital notation. So in orbital notation, unoccupied orbitals are represented by a line with the orbital name written underneath it. Electrons are each represented by an arrow, up and down to represent spin, and because docs and slides and all those won't allow me to do a one-headed arrow, it shows as a two-headed arrow, but it's most commonly seen when it's handwritten as a one-headed arrow. So we would show an orbital that has 1 electron, like that, and an orbital that has 2 electrons, like that. Well, let's start off with something simple. How about, an atom that's got 5 electrons. Now, what's the lowest energy orbital available? Well, 1s. So we would write the 1s orbital here, and we know that we can fill it, 1, 2. We still have 3 electrons to place. So what's the next lowest energy orbital? Well, it's 2s, of course, and we know that we still have 2 electrons to place. Now, we're up to the 2p subshell, and there's a funny little thing here. When you draw any of the orbitals in a subshell, you gotta draw them all. So I'm going to draw 2px, 2py, 2pz, even though I know I only need to place 1 more electron. That's the orbital notation for an atom with 5 electrons. Let's do an atom with 7 electrons. I've pre-drawn my orbitals here. So with 7 electrons, I know that I've got 1, 2, 3, 4, and then I've got 5, 6, 7. Why am I drawing it that way? Well, remember that each orbital that has equal energy will get 1 electron before any orbital takes on 2 electrons. Let's do a slightly more complicated example. What if we have something with 17 electrons? You know what I think would be really helpful? I think the subshell filling diagram would be really helpful. Okay, if I've got 17 electrons, we start off with the 1s. So let's start by drawing the first 4 subshells. Will this be enough? Well, let's fill these and see where we're at. So I go 1, 2, 3, 4, 5, 6, 7, remember the rules, 8, 9, 10, 11, 12. Nope, still not enough. So I'm going to go to the next subshell to fill, which would be 3p. Now I have 5 more electrons to load here. 1, 2, 3, 4, 5. Hey, there's an atom with 17 electrons. Should we do one weird one, one difficult one? Okay. Let's do iron with 26 electrons. Let's get our subshell filling diagram. So I've gone as far as the 3p subshell, and let's start filling. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh boy. I got 8 to go. Well, what fills after 3p? Remember, this is when it gets weird. 4s. So the 4s subshell fills next, and that's 2 more electrons. So now we're up to 20 electrons, and what's going to fill after that? The 3d. So I have 20 electrons here, and I've got, 6 electrons left to go. How do we do this? Well, 1, 2, 3, 4, 5, 6. Not so hard. Take the practice sheet that you'll find in the folder and do the orbital notation for every single element on the practice sheet. Then you can watch the next video, learning electron configuration notation, and practice those. Get going.